Let's walk through a detailed worked example in multinomial naive Bayes. So for this example, I put up here the equations for naive Bayes. So the probability of a class is the number of documents with that class over the total number of documents. And the likelihood of a word given a class, we'll just do simple add one smoothing, the count of the word occurring in that class divided by the count of all words in that class, and with add one smoothing. And let's assume that we have 4 training documents, 1, 2, 3, 4, and 1 test document. And here are the documents. They're simplified, obviously, documents. This document has only 3 words, Chinese, Beijing, Chinese. And this document has 3 words, Chinese, Chinese, Shanghai, and so on. And let's say we have just 2 classes, Chinese and Japanese. Our job is to do Asian news topic classification. So 3 of our training documents are in the class China, and 1 of them is in the class Japan. And our question is, what's the class of this test document? All right, so let's do some computation. First thing we're going to do is compute the priors. So we need to compute P of C, the class China, and P of J, the class Japan. So P of C is how many times does the class Chinese occur in our training set? 3 out of how many total classes are there in our documents are there in our training set? 4. So 3 of the 4 training documents, so that's 3 out of 4, are about China. So our prior probability of a document being in the topic China is 3 out of 4. How about Japan? Well, there's only 1 document in our training set about Japan out of the 4 documents, so the probability of Japan is 1/4. So we've seen how to compute our prior probabilities here. Let's move on to the likelihoods. Let's compute each of these probabilities. What's the probability of the word Chinese given the class C? What's the probability of the word Chinese given the class J, and so on? All right, so the probability of Chinese is how many times does the word Chinese occur in our training set of documents that are in the class China? Okay, so this word Chinese, how many times does it occur in these 3 documents? 1, 2, 3, 4, 5. So we have 5. We have add one smoothing, so we're adding 1. And how many total words are there in our training set? 1, 2, 3, 4, 5, 6, 7, 8 that are in our Chinese class. And then we're going to add the vocabulary size V. Again, we're doing add one smoothing. So we'll add the vocabulary size V, and our vocabulary is 6. 1, 2, 3, 4, 5, 6. So that's 5 plus 1 over 8 plus 6, or 6/14, or 3/7. And we'll do the same thing for the word Tokyo. Tokyo doesn't occur at all in our 3 classes. It has a count of 0. But we're doing add one smoothing, so we'll add 1. And it's the same denominator, the same number of total words and vocabulary size in our Chinese class. So that'll be 1 out of 14. And the same exact thing is true for the word Japan. Doesn't occur in our training set. And in our, now let's turn to the class J for Japan. So now the word Chinese does occur once. And then we'll do, so it's once plus 1 for add one smoothing. And we'll divide by the count of the words in this class. And there's 3 words in this meta document of 1 document. And then again, we add the vocabulary size. And so we've got 2/9. And we can compute the next 2 numbers the same way. So now we have our priors and we have our conditional probabilities. We're ready to decide which class is more likely for our test document. So for our test document, we'll call that document 5. We need to compute our prior and our likelihoods. So our prior is 3/4. The prior of being Chinese for document 5 is 3/4. That's the prior for Chinese, times The word Chinese occurs 3 times, 1, 2, 3, and each one of those gets the probability of Chinese given 3. So it's 3/7, 3/7, 3/7. Then the word Tokyo occurs. That's got probability 1/14. Then the word Japan, 1/14. And we multiply all that together and we get approximately 0.0003. Notice that we say that this probability is proportional to this product because we are computing the argmax between these two classes. We're computing the class which maximizes the product of the two probabilities, but the actual probability has a denominator in it. It would have to be divided by P of the document. And we're just skipping that part. And so we're actually not computing the probability, we're computing the numerator of the probability. But since document 5 has the same P of document 5 in both the Chinese and Japanese classes, we're just going to not compute that. So we have a proportional to and not an equal sign here. Good, and then for the probability of class Japanese given document 5, now we have the prior for document Japanese, and we multiply that by the probability of Chinese given the class Japanese. So that's 2/9 times 2/9 times 2/9. And then the probability of Tokyo given Japanese, that's another 2/9. And then Japan given Japanese, another 2/9. And so we get a slightly lower probability. So in this example, our model would choose which class for this document? It would choose Chinese because 0.003 is bigger than 0.001. Now we've talked about naive Bayes where we're using each word as a feature and we're using all of the words. But in lots of examples of naive Bayes, we're going to use richer features than just words, and we're going to use specific kinds of words and other things. So Spam Assassin is a naive Bayes classifier for spam detection, and it looks for things like, is the phrase generic Viagra mentioned? Is the phrase online pharmacy mentioned? A little regular expression for millions of dollars mentioned? Is there a phrase impress and nearby the word girl? Does the from have a lot of numbers in it? Is the subject in all caps? So all sorts of different features that we can use to combine. And you can look at the Spam Assassin website to see a common set of features. So in summary, naive Bayes is actually not that naive. It's a very fast algorithm. It has low storage requirements. It's pretty robust to irrelevant features. They tend to cancel each other out. It works well in domains where you have lots of equally important features, and this turns out to be a problem for some other classifiers. In particular, decision trees, which have some advantages in numeric domains, don't work well if lots of features are equally important. If the independence assumptions hold, if the assumed independence is correct, then it turns out that naive Bayes is in fact the optimal classifier for a problem. Of course, that's rare that these independence assumptions are really true, but if they happen to be true or close to true, it turns out naive Bayes is in fact optimal. And in general, naive Bayes is just a good dependable baseline for text classification, although we will see other classifiers that give much better accuracy.